was just copying over some code I had. So I'm at my office. I'm at a different computer. So, okay. Right. Oh my. Two computers. So let me share my screen. Okay, hopefully you see that. You can hear me. So, so we did that poll, or Veronica did that poll yesterday, and the two areas that came out was just more material on Tellurium Roadrunner, and then something on fitting. Veronica did a little bit on fitting the last 2 hours. So I'm going to cover some other topics, which are usually pretty relevant to modeling, and also show you some fun tricks you can do with Python and combining it with Roadrunner and Tellurium. So let's talk about, first topic is, let's talk about the steady state. So I guess the best way to do this is for me to actually do the demo. Actually, come to think of it, might as well just do an actual demo. So let me do, let's go to the bottom of this and actually do a demo. I'll save all this to the drive. Okay, so what I'm going to do here now is I'm going to load a model. Okay.
You may have to do your imports. I don't know how much of the previous.
Yeah, it's probably imported them already, but I'll do it anyway. It's always good practice to do that, I guess. And then what I'm going to do is, just so we can get the idea right, what we mean by steady state. So I'm going to do this. Oops. I'm going to do that. Just to do 3 reactions. I don't care what the last one goes to. Okay, so there's 3 reactions, and then I'll set up some just from random parameter values. And then I'll set up S1 equals, say, to 10. Okay, and I'll run a simulation. 50, 100, dot plot. There you go. Okay. Mistake. Okay. And we do that. Okay. So what we see here, we've seen something like this before. Everything seems to drain away from S1. This is just a linear pathway. Everything seems to drain away from S1. Maybe I should, let me name one of these fluxes, replot, or rerun it. And then let me have a look at J0. J0 is actually, it will get smaller and smaller. In fact, it would tend to 0 as time goes to infinity. This is not a very useful model to work with in cells. Cells don't, I mean, if cells do this, they're pretty much dead. And instead, you know, cells are more dynamic, they're at steady state. And basically the way we do that is to create a steady state is we fix the boundaries. So there's only one named boundary here, which is S1. I've just put a $1 in front of it. There's another boundary here, but it's essentially fixed anyway because it's not listed. If I run this, I get a completely different plot. Okay, and if I look at the J now, I actually get a finite flux of 1.0. Okay, so this system's at steady state. In fact, there's a call called RDV, which returns all the rates of change. So the rate of change of S1, S2, and the rate of change of S3, and they're 10 to the minus 8 and 10 to the minus 5. Now, there's a much quicker way of getting to the steady state, and that is by just actually calling a function called steady state. I'm going to print this because it actually returns a number. And that number, you can see the number here, if you can see it, is 10 to the minus 16. It's pretty much 0. That number is essentially the sums of squares for the rates of change. So the closer that number is to 0, the closer you are to steady state. So anything below 10 to the minus 5 is pretty much steady state, and this is 10 to the minus 6. I can actually run it again, and it'll actually might get even closer. Yeah, it's actually at 0 now, because it started from the computation it just did, and then tries again to compute the steady state. This time it got it exactly right. So S2 is the steady state level of S2, and S3 now is at the steady state level of S3. Okay, and J1, of course, is now steady state flux 1.0. So the function R steady state is a very quick way of getting the steady state. It means you don't have to run a simulation. All right, you can just compute the steady state immediately. And it's much faster than running a simulation. And sometimes you're not quite sure when you run a simulation whether the entire thing has reached a steady state. You might, what can happen is some of them have reached steady state, but other ones haven't. And you might have to run it for a long time for all of them to reach steady state. And that can be inefficient. So steady state is you do a completely different algorithm. It's similar to the one that Compartments uses. Actually, we have two actually built in. That's how you can compute steady state pretty quickly. So if you were to try, I guess this example, let me take the boundary off. So now it's back to the closed system, right? And now I would ask for the steady state. Yeah, I didn't want to do that one. Let's try something else. What I want to show you is what happens when there isn't a steady state. What is found is the thermodynamic equilibrium state. Let me see. What do I do here?
Herbert, can you mention what is technically the return value for the steady state function again?
It's the sums of the squares of the dx by dt's.
Okay.
So each dx by dt is squared and summed.
Got it.
And they all go to 0 as it approaches steady state.
At what time point? At the last time point of
There's
the
no time
simulation?
point. There's no time points. So when you call steady state is a completely different algorithm. It's basically a nonlinear solver. And so there's no time at all. It finds the solution, basically. And the solution is the steady state.
Okay.
It's basically solving a problem of this form, f of x equals 0. So it sets all the differential equations to 0. So it has a set of nonlinear equations and then solves them using root finding algorithms.
Solves them for the variables?
Yes.
For the state variables?
The state variables, yeah. All the state variables. So in fact, there's another one. Get nay, how's this go? No, let me see. Get here we go. There's another method called get steady state values named array that will compute the steady state and return all the other concentrations. So in this case, because the system is closed, so everything is 0. Okay, so let me just take that back here, make it an open system again. And then I'll do this. So now it returns S2 and S3 because it names them. It names the array, and it tells you that the steady state level of S2 is 2.94 and for S3 is 4.347. All right. So yeah, there's no time involved. There's no time computation involved here at all. It basically solves the system of nonlinear equations.
Now, often that will be as if you ran the simulation for a really long time, but technically it is not.
Correct. Yeah. And let me get this model because this model didn't have a steady state. And I want to show you what happens. So this model, right, S2 goes to infinity, or looks like it's going to infinity anyway. If I try to ask it for the steady state, you actually get an error. So it's saying possible negative, I mean, this time it says the runtime error is possible negative concentrations in solution. It's not quite sure what's going on, but it cannot find a solution. That's because there's no steady state. Because in this case, S2 is going off to infinity. Okay. All right. Yeah, and often if there are errors in your model, you'll also find problems in computing the steady state as well. Okay, and this is an example here. So maybe I should show you this one as well. Show you what happens with this one. This is where an error was made in the rate law. So this rate law here was incorrect. It should have been times S3. If I just run a simulation, let's see what happens. I can't actually remember what happens. What did I do? Invalid. What did I do wrong here? Oops, sorry. So if I run this, well, it's going completely negative, right? This is a crazy model. If I ask it to compute the steady state, now says another error. It says something called the Jacobian matrix is singular, failed to converge to steady state. Okay. So if you see any scary messages like this, it probably means there's something wrong with your model. Either the model is going up to infinity, or you're getting negative concentrations, or there's something very crazy going on. All right. Okay. So this slide here just tells you what the this value that comes back from steady state is basically the distance from the steady state. So you can do a double check, you know, to make sure it looks okay, just by printing the value out. Okay, so so what can we do with this then? Let me see if we had a hold on, let me go back to the slides rather than go off message. Okay, so that's basically the steady state. All right, so I use it a lot, you know, often do steady state calculations. For large models, you might ask it to do an initial time cost simulation to help it. We do that already, but sometimes you can give it a help. It actually has an algorithm where it tries multiple times to find a steady state if it has difficulties. So it does try its best. But for simple
there's a question
models,
about limit cycles.
what's that?
There's a question about limit cycles. Is there a similar built-in function for information about limit cycles, or for that you need to simulate?
All right, in that case, let's do one.
All right.
Okay, let me take this one.
And yeah, we'll try to put
work.
the notebook in the slides on.
So what I'm going to do is I'm going to change this model so that there's negative feedback coming back from S4, okay? I'm going to put a hill coefficient on this so that it's, and I need to change that to S3. Set n, let's set n to n equals negative to 10. Okay, let's see what happens. I just made this model, didn't like, oh, okay, yeah, ki, no value for ki. Let's give that number. Okay. Okay, almost a wiggle. Let's see if you can push it even more. Let's take that down there. Let's take that up there. Let me see if I got enough. Let me put in another. I'm going to put in another stage just in case it's not enough. Now this is expected K5. K5. Now I've got K4.
And your last step should be K5 times S5.
Oh yeah. Correct. Let's see if this does it. Oops, K5 is missing a value.
Oh yeah.
There you go. Okay. That looks like it's oscillating. To make sure, let's push up the time. There you go, definitely oscillating, okay. So the question is there a steady state here? I mean, there actually is one, because let me instead plot what's called a phase plot. So I'll plot S2 versus say S5. So that's a phase plot now. You can see some of these straight edges. So I'm going to push that up to 5,000 so we get some pretty smooth curve. So this is the phase plot. So I'm just plotting S2 against S5, and what we're following along here is time. So this tells us the values of S2 and S5 as time progresses, and we can see that you get this convergence to what's called a limit cycle. Okay, and right in the center of the limit cycle, there is actually a steady state, but it's unstable. Now, I can actually access that steady state. I can actually find out what that steady state is. just by calling, oops, sorry.
Yeah, caps lock on.
Yeah, I know. My little finger doesn't work properly. Okay, look at that. It seems to have found a steady state. So let's have a look at the value. Let's have a look at the value for S2. It's 0.416. So S2 here is on the x-axis, and 0.41 is roughly here. So it's definitely not on the cycle. So it's somewhere inside the cycle. The same would go for if I did S5, 0.83. And 0.83 is on the y-axis is about here. That's also in the side. So that's basically in the center of this limit cycle. Characteristic of the steady state in a limit cycle is that it's unstable. And I can actually get the, let's see if we get this right. Oops, sorry. I can actually ask for those of you who've done some stability analysis, not that one, will know, come on, do it. We'll know that you can check the stability of the system by looking at the eigenvalues. And if you find positive eigenvalues, at least the real part, you know it's unstable. So there's a method we've got called get the eigenvalues. Full basically means get, well, I actually can't explain that. It involves more of an advanced topic, but you would call get full eigenvalues. Basically returns every eigenvalue in the system.
Someone's curious about what would happen if you simulated starting at this.
Yeah, so that's a good idea. We'll do that in a sec now then.
Yeah.
So you'll notice that there's a real part here that's positive and a real part here that's positive. That means its system's unstable. Okay, so the question was, what happens now if so let me go get steady state named array. Oops. So those are so I need to grab these.
Isn't the model just set there?
What's that?
Isn't the model, if you run the model to steady state, doesn't it set those values anyway?
Oh yeah, it does actually. Yeah, you're right.
Okay, yeah.
Yeah. Good point. Let me get rid of this then. So now let's do a simulation then. I'll simulate.
Equals, not minus.
Oops. 0, 100. Let's do 50, 100. And then r dot plot. We should see straight lines. And there they are. Now, to show that it's unstable, I will take S2 and perturb it. Okay. And I'll rerun the simulation. Plot. And now you see it, it started to diverge, it's diverged and it's now oscillating again. So, so you can look at the stability of a system by looking at the eigenvalues, and you can, mess around. This is one of the nice things about Python, of course. It's very interactive, right? You can go back and forth, try things all the time. And you can do the face plots here and see what's going on and so on. Okay. Any more questions on that? We showed you how easy it was to make an oscillator, right? Just stick some negative feedback in, have sufficient steps, make the Hill coefficient here high, and have a low Ki, and you've got an oscillator. So
someone just mentioned that they had learned that kind of stability is orbital stability. It's a new.
I've not heard that phrase.
Yeah.
It's normally called limit cycle stability, and or maybe the stability point itself is called orbital stability. I'm not sure. Okay.
Okay.
Yeah. All right.
Yeah. And the limit cycle, yeah.
Okay. Now the other thing I want to talk about is, there's just to give you an idea about steady state, steady states. What I have here is a very simple model. X0 goes to S1, S1 goes to X1. X0 and X1 are fixed, okay? I'm going to have some very simple rate laws. For V1 is K1 times X0 and V2 is K2 times S1. From that, I can construct the differential equation. which is this, right? So it's actually, yeah, it's that. Yeah. What I can do though is I can plot both these rate laws as a function of S1, and so that's what this plot does. So the first thing is the x-axis is S1, and the y-axis is the reaction rate, either V1 or V2. Now you notice that V1 is not a function of S1, but it's a fixed value, K1 times X0. So that's why I get a horizontal line. So this horizontal blue line is V1. The V2 is given by these various colored lines, red, green, and orange, and they are different by the value of K2. So if you go back to here, you'll notice that V2 is a straight line function of S1. So, but it's a function, the slope is K2. So thus I'm getting different slopes. Now where these lines intersect on the blue line, that's the steady state, because that's where V1 equals V2. So this is a very easy graphical way of looking at what a steady state is. Okay, it's when all the rates balance and you're at the steady state. The other way of looking at a steady state is to actually do it algebraically. So if I take the differential equation for this system, ds1 by dt, it's this. So it's the v1 minus v2. To compute the steady state, I've just set the whole differential equation to 0 and then solve for S1. And that's my steady state level of S1. Okay. Now, most of the time you can't do this, of course, because a lot of the systems are nonlinear. And I doubt if you could do it for this system, which is why we generally always end up doing simulations, because we can't do it analytically. Okay. All right. So another thing that you might want to do a lot, especially if you do metabolic modeling, is to look at sensitivities. And I'm thinking of this from the point of view of metabolic control analysis, but it's basically just sensitivity analysis. So a sensitivity, there's two different kinds of sensitivities. There are the unscaled ones and the scaled ones. So these are the unscaled ones. It's literally just a derivative of some observable with respect to some parameter. Okay, now the observables can either be the rates for particular steps, or the observables can be the species levels. The parameters can, what you're looking at the sensitivity with respect to can be anything, but in metabolic models, it's often the amount of enzyme at a particular step. Okay, so a sensitivity measures how much a system variable depends on a system parameter or input. And there are both steady state and time dependent sensitivities, and we support both of those. One issue with these unscaled sensitivities is that they have units. So the reaction rate will have a unit, the parameter will have a unit, so you'll have units. So that means comparing sensitivities between different systems becomes very difficult, because if the person has used different units, and you can't do the comparison. And this is particularly the case if you then try to measure these experimentally, because who knows what units they're using. So it's more common to actually look at scaled sensitivities, all right, the scaled ones. So the scaled ones are just the same derivative, but now multiplied by the parameter and divided by the rate. Or in the case of the species levels, we multiply by the parameter and divide by the species. So basically just the scaling eliminates the units. Okay, so these are unitless sensitivities, and it makes it a lot more convenient for experimentalists. So for example, one of the labs we work with, they can make percentage increases in expression rates and measure percentage changes in metabolites. Trying to compute absolute changes is possible, but very expensive experimentally. So the scale sensitivities are therefore much more useful. The other nice thing about scale sensitivities that I just implied is they can be interpreted as ratios of percentages. So it makes them very, as I said, very friendly to experimentalists. Okay. Okay, so in Roadrunner, you can compute both scaled and unscaled sensitivities. Okay, so let's go to a model. Let's see. Yeah, let's take this model, shall we? I'll make a copy of it, And what we'll do is I'll take out the negative feedback. Okay, don't want that. So there's no n or ki. It's just confirmed. And I'm not going to not particularly interested in plotting particular ones. Okay, there you go. So that's the model there. And what I'm going to do is I'm going to calculate the steady state. Okay. So it's computed the steady state, and there's the output from the steady state, 10 to the minus 16. Okay, now I can now compute the steady state sensitivities of this system. So I could ask, for example, how sensitive is S4, the concentration, the steady state concentration of S4 with respect to, say, K1. That's really easy to do. There's a method called get CC, which these are the scaled sensitivities, and it takes two arguments, which are both strings. One is the first string is what are you observing? Well, let's say was it S3 or S4? I can't remember. I'm going to observe. Yeah, let's do S4. I'm going to observe S4 as a result of changes to K1. So if I run that, I get a number. It's basically 1. So it's saying that if I change K1 by 1%, I'll get a 1% increase in K4. Okay. I can pick other ones. I can pick other parameters and see what they do. That one is 0 for some reason. S2 on S4. K2 on S4. Okay, apparently it's 0. Okay. K3. Also 0. Let me just double check this. What's it doing?
And the K1 is just dominating. If the K1 is 1, then that's everything that.
It's not behaving itself. Oh, there you go. Oh, right. Okay. So all the Ks are. Oh yeah, of course, yes. It's because all these steps are irreversible. So if I change K2, it has no effect on S1 because there's no way for the change to propagate back to S1. So if S1 stays the same, the flux, of course, the flux through the first step has to stay the same. And the only way for the flux to stay the same in the second step is if S2 now stays the same. The same argument then goes for S3 and S4. Therefore, everything stays the same if you perturb anything below K1. So all the sensitivities with respect to K2, K3, K4, K5 have to be 0 because of that. I can also look at the unscaled ones. We also allow you to compute the unscaled ones. So you just put a little u in front. And now you get these funny numbers. So now these numbers are units now. This would be concentration per second, concentration time, because K1 has units of per time. And we're dividing by K1. The K1 is in the denominator, so it becomes concentration time, all right? So you get these strange numbers, right? And it's very difficult then to interpret these from an experimental point of view. Okay.
Just real quick, the CC stands for control coefficient, if anyone was curious.
Yeah, so there's a technical term for these sensitivities. They're either the flux control coefficients or the concentration control coefficients. So we just use CC from control coefficient as we could have used the word sensitivity, I guess, but in the end, I used CC, so. Okay, let's go on here. So we've done that. Yeah, so what I'm going to do now is I'm going to use this utilities package called TE-utils. So you'd have to install that if you don't have it, all right? Just using a pip install. But what I want from here is let's see, get linear chain. I want to get the the random network generator. So if I go print model, it actually returns an antimony model, antimony string. You see there it is. So this is a random linear network of 12 steps that it generated. Okay. So I can load this, of course, into tellurium, and then I can ask for the steady state. Let's see if there's a steady state. It should be. Yes. Okay. I can get the name. I can get the steady state named values. I can get all the steady state numbers. Those are all the steady states for this system. Okay. Now, so that's what I basically did there. Okay. So if you want to see what let's do a reset, and then to show you what the trajectories look like. Okay, that's all the data, and that's what the trajectories look like for this random network. Okay, all right. What can I do with this? Well, I can compute all the control coefficients as before. So there's some parameters in here, for example. We have let's say K40. These are all reversible now, so I can go r.get cc s4 K40. I'll get the sensitivity for that one. There it is, 0.01339. But better still, I can actually get the entire matrix, actually get the scaled, all the concentrations. This actually returns all the sensitivities in the entire network. So every step with respect to every species. So if I perturbed step J5, for example, and I observed S3, it's telling me to begin with that it's negative. That means if I perturb J5, the concentration of F3 will decrease, and it decreases by, if I were to increase J5 by 1%, I get a 0.078% decrease in S3. So this is the entire sensitivity matrix for this pathway. Okay, so that's what I've got there, and you can get the concentration ones or the flux ones. I got the concentration ones because they're usually more interesting. Okay. Now, what I can do if I want to, let's say I wanted to pull out, is an example of pulling out a particular. Say I wanted to see how the sensitivities of S4 change. And I want to plot a histogram. So let's do matplotlib, matplotlib type plot as PLT. And then what I'll do is let me pull it out as, let's call it CC. So I got the entire matrix. I can then go PLT bar range. I have to now give I'm going to do a bar graph. So was 12 of them. And then I'm going to extract. So I want to extract a row, okay? So I basically want to extract, where did it go? It disappeared, but I want to extract a row. Let's extract the 5th row and all columns. Okay, so I'm using this slicing technique here. So the first one is what rows you want to pull out. The second one is what columns. So I want to pull out the fifth row, but all columns along that row. Okay, so if I do that, what do you mean is not scriptable? That's right, you're right. It's supposed to be expects a list here, which is the ordinal value along the x-axis. There it is. So that's how the sensitivities along the how the sensitivities for species S5 along every step, how the sensitivities change. So you can see it's most sensitive at the beginning, approaches 0 towards the middle, and then goes negative. Right, so it's basically telling me any perturbations downstream of S5 will pull down S5. Any perturbations upstream of basically step 6 will increase S5. Okay, so you can do that kind of thing. Okay, so let me get the flux ones, because I'm going to show you something. So what I'm going to do here is I'm going to compute the flux ones, all right, and then that should be 12 now. I'm going to plot the range of flux control along the pathway, right? So this is step 0 all the way up to, well, should be 11 or 12, all right? So it's telling me that perturbing the first step increases the flux or the reaction rates through the pathway the most. And then it just starts to drop. And in fact, steps downstream appear to have very little effect on the flow. So if you were a metabolic engineer, you wanted to increase the production of this, whatever this pathway is making, you would engineer the first step and maybe the second step. You wouldn't bother engineering all the steps downstream because they have no sensitivity, okay? What happens, however, if and this is the case in a lot of amino acid biosynthetic pathways. So a lot of amino acid biosynthetic pathways are sort of linear, but a lot of them have negative feedbacks, okay? So what would happen if there was a negative feedback? And so this is, I've got this, let me take this model. This model has a negative feedback for me. Okay. And then I'm going to do the same thing then, ask it for the steady state, compute the sensitivities, and then do the same plot. Okay, so you see there's a completely different picture. So without negative feedback, a lot of the sensitivity appears to be in the front of the pathway, but with negative feedback, most of the sensitivity goes to the back of the pathway, the end of the pathway, okay? And so now if you're an engineer, there's no point engineering the start of the pathway, you should be engineering the end of the pathway, okay? So you can study things like that. And it just gives you a summary without feedback, with feedback. This is something that a lot of engineers forget, because the negative feedback will usually is probably on step 0, and the regulated step has the least sensitivity. So if you go to a lot of the textbooks, they'll tell you should be engineering the regulated step, when in fact they're wrong. You should be actually engineering the last step of the pathway just outside the feedback loop. If you try to engineer the regulated step, nothing will happen. And that's been shown many, many times experimentally. So, okay, you can now do some lots more clever things. What I've got here, I couldn't run this on Colab because it took too long. But what I've got here is I'm basically sampling the sensitivities. So I've got a model here. I hope you can see it, a model. I should actually have it. Oh yeah, I don't have it here because I couldn't run it. Let me see if I have it here. Yes, I have it here.
Or you're gonna have to share your spider screen.
I know, I'm just about to switch over.
Yeah.
I'm just trying to find it. Where the hell is it? Yeah, oh, here we go. Okay. Could you see my spider?
Yep.
Yeah. So I got a simple model here, 4 steps, okay, both reversible, some initialization, run a simulation. There's no point in doing that actually. What I'm going to do is I'm going to compute the steady state 1,000 times, okay? And each time, and I got a loop here that loops over that 1,000 times. Each time I compute the steady state, I'm going to randomize the values of the rate constants. So there's four rate constants here, 1, 2, 3, 4. And I'm going to randomize them using a uniform random number generator with an upper limit of 50, okay? Then when I do that, I'm going to ask it to compute the steady state. I put this around a try except block. That's perhaps not something we've done, but it's basically an error trap, because sometimes you may give it values of parameters where it finds it really difficult to find the steady state, and then it gives an error. So what I'm doing here is I'm basically trapping any of those bad models and just ignoring them, okay? That's all that's about. So I randomize the parameter values and then compute the steady state, and I collect all the sensitivities, and I accumulate all the sensitivities, And then in a long array, so I have this big list, and I accumulate the sensitivities at each step, and then I take the mean. Okay, I compute the mean, and then I'm going to plot a histogram for the distribution of the sensitivities at each step, and that's what this plot is here on the right. So what this plot here is the y is the frequency, and the x-axis is the value of the sensitivity. Now you'll see there are actually 4 distributions: there's yellow, green, blue, and pink. The yellow corresponds to the distribution of sensitivities in the first step, and the pink corresponds to the sensitivities in the last step. And you can see that in a range of random models, random parameter settings, again, it shows that most of the sensitivities in the first step, and the last step contains the least sensitivity, but is also spread out a lot. Okay, so you can do this. Is one of the advantages of using a scripting language, is that you can put together your own analysis, do your own plots, and that can be quite useful depending on what research you do. Let me close that off. Let me go back here. So that's what that was. Okay. The other thing you can do with these sensitivities is we have a series of methods to let you plot heat maps. So we've got here, so let me do it here. So instead of plotting a bar graph, actually, let me do it on this one. So instead of plotting a bar graph, I shall plot a heat map, okay? So plotting, plot, so there's a whole bunch of little things here. Concentration control heat map, here we go. It needs the Roadrunner instance, but then I can run this and I get a heat map. There aren't many steps in this pathway. It might be better if I see. So let me see what we got here. 12. Let's generate it. Let's generate 40 steps. Okay. So it's 40 steps now. So it's much bigger model. Okay. Much bigger model. And we load it up. Okay, just compute the steady state to make sure we can get the steady state. Yeah, we can. Then I'll go back down to here and I'll ask it to plot the heat map for that. Takes a bit longer because there's a lot more steps. What's taking the time here is actually doing the graphic, and yeah, that didn't work out too well. It needs to be a bit bigger. And I got a feeling I have big size here. Let's try to make it bigger, shall we? Okay, it takes a little bit of effort to do the plot. No, that wasn't too good. Let's do 16. Anyway, I've got some heat maps if I scroll up, but just to show you, maybe this is big enough. No, it's still not big enough. Let me maybe scroll back up here and I can show you some heat maps. Oh, here we go. So these are the kind of heat maps you might get. So this is actually the flux control heat maps. So the red ones, of course, are the most sensitive, and the light ones are not sensitive at all. If they're blue, it means they're negative. Red means they're positive. So you can get a quick snapshot of the distribution of sensitivities in a pathway. This happens to be the flux. Let's do the concentration instead for this one. Let's try that. Plot is not, whoops, concentration. There you go. Okay, that's a bit better. So these are this is how sensitive the concentrations are to the different steps. We got our 11 steps. This is the end step. This is the front step here. So you'll see in fact, it's split through a diagonal. All the ones below the diagonal are positive, and all the ones above the diagonal are negative. This reflects the fact that perturbations at a particular point mean that everything upstream will decrease in concentrations and everything downstream will increase in concentrations. And that's what you're seeing here in this diagonal, that divides the red from the blue. Okay. Okay.
There was a quick question.
Yeah.
You said at one point you were like, "I'll add in some negative feedback," and then put in a formula. And it was like, "Oh, what is that formula?"
What is that magic formula? Yeah,
Yeah.
that's a good question. The magic formula is this. So I know, for example, that negative feedback means that if I increase the concentration of something, the reaction rate has to drop. Okay. And the way to do that is to put your signal molecule into the denominator, into a denominator. So as the denominator increases, the entire expression decreases in value. Okay. Now you'll notice there's a +1 on here. This is to avoid divide by zeros, because if S5 goes to 0, I'll get a divide by 0. So I maintain a non-zero denominator by always adding 1. Okay. The other thing, then, I have this to the power. That's to ensure that changes in S5. This is to ensure that the reaction rate is very sensitive to changes in S5. If I put a 1 in here, no, hold on. If I put a 1 for n and I run this, it's stable. So one of the requirements for oscillations is that you have to have sufficient delay between the signal and where the signal acts. But the other factor is that any changes in the signal have to amplify. And the only way one way to amplify is to have a power factor here. And if I say slowly increase this, you'll see it starts to becoming more and more oscillatory. So if I increase this to 5, it goes to there, go to 7. In fact, there's a nice theorem that says it has to be 8 or above. So if I do 8.5, maybe, it's probably actually oscillating now. But it's above 8. I think it's 8. It is. It'll start to oscillate, and that is a nice proof. You can actually prove it mathematically that n has to be at least 8. I think it's 8 point something actually. Anyway, so does that answer your question? The basic structure of the rate law. I needed something that when the signal increased, the rate went down. I didn't want any funny divide by zeros, so I added 1 to the denominator term. And the other thing, I wanted high sensitivity, so I put a power there. This divide by ki what that can do, it can move the sensitivity where the sensitivity occurs. That's all that does. And the lower that is, the better it is. So that help that with that question.
Yeah, I think so. Although there's a lot of concepts here.
I know. I told you
why?
More advanced.
So you initially tried this with S4, and then we're like, oh, I should add another step.
Yeah.
If you did go back to S4 and had a really high end, would that work? Or
yeah, there's another theorem, which is there has to be a minimum number of steps. No, it doesn't matter how high your n is. Well, yeah.
That's interesting.
Yeah, it doesn't matter how. I don't know what it's doing there. Oh, this is a phase plot. That's fine. Yeah.
That's phase plot. Yeah.
Yeah. Let me show you for sure by not doing the phase plot. It's stable. I mean, it doesn't matter how high n is, it won't oscillate. It's to do with the delays. I mean, it's a bit more subtle than that, but it's to do with the delays between the signal and where the signal acts. Okay. If you have enough of a delay, it'll ring like a bell. Okay. So,
and similarly, why do you have to have negative feedback and not positive feedback?
If you have positive feedback, it just locks into one state. If I can do that, actually, if I do there's a positive feedback. Okay. So now as S5 increases, the rate increases. Okay. That's usually bad news. Yeah, nothing happens. I think it's because I need to have one thing at least a little bit, I think. And this will probably have 2 steady states, one at 0 and one probably at infinity. Yeah. All right. So if it's at 0, that means they're all at 0, right? S5 is at 0. If S5 is at 0, this rate is 0. And therefore, all the rates then are 0. And it just sits at 0, right? This is what we're seeing here. Everything is at 0. If I put even the tiniest amount, let's not simulate too far. You might be able to see the, let's see, I'm expecting an explosion. Well, yeah, maybe that's not enough. Should explode. Okay, it's exploded. There's obviously a point where it just explodes. Like it'll explode as the negative feedback.
The positive feedback.
Yeah. Oops. Let's see, where's maybe the explosion happens at the transition between at 1. Oh no, it happened there. Okay. There's a very sensitive point here where it either sits at 0 or it sits at infinity. All right, I can't get it. What's happening is with S3 is now finite. That means it makes S4, which then makes S5. Now it starts making S5, but that's a positive feedback. So that increases the rate of this step, which produces more S2, which produces more S3, and ultimately more S5, which then increases the rate even more, and so on. And it basically, you get this uncontrolled explosion. And I thought I could get it really at the point where you could see it exploding. I guess not. Too sensitive. Yeah, maybe. Hold on. Oh, okay. It's getting close. Yeah, it's very sensitive. All right, look, it's looks. You see that little tweak there? It's about to explode. No, that was it. Yeah, it's just all of them are going to go off to infinity. Okay. So yeah, you don't want positive feedback. Now, if you combine positive feedback with negative feedback in a certain way, you can also get oscillations. That's another story.
Is the formula you use the only way of writing negative feedback? I assume there's infinite ways, but there's like more, some that are more reasonable than others. Yeah,
you can implement it in many ways. The idea is that when the signal goes up, the rate must go down. You've got to implement that behavior somehow. Okay, so you can imagine probably lots of ways of doing that. Or they'll probably all be very similar though.
Are there any that are, is there any theory about the actual biology involved, like what formula would match that better? Or
yeah, you have an allosteric enzyme, for example.
Yeah, and are there formulas associated with that, like a Cayless method or something? Or?
Yeah, and in fact, glycolysis, for example, PFK has a feedback from AMP. Now, normally you don't expect glycolysis to oscillate, but under certain conditions, you can make it oscillate because of the negative feedback there. And you can model that enzyme using an allosteric rate law, okay? Like the ones we mentioned briefly on Tuesday. But remember, you remember the idea is not to make it more complicated. You want to know what's the simplest model that will give me the results I'm looking for. And if this sort of simple thing is good enough, right, and it predicts everything correctly, then that's good enough. You don't need any more elaboration. Okay, so
someone was also asking about the error message you got, the convergence test failures.
Oh yeah. It's what's happening is the integrator is trying hard to solve the differential equations, and it's just failing to do so.
Because
so
everything is going to infinity.
It's not converging to a solution. Yeah. It's going to infinity. That's why the model is going to infinity. All the concentrations are going to infinity because of the positive feedback. Yeah.
All right.
All right.
You have a couple more specific questions. One again, 1 plus exp s5 divided by k1 ki.
What?
So in there, yeah, 1 plus exp s5 divided by ki. was wondering if that like e to the S5 divided by ki.
I don't have an e here. What
exp.
E?
The exponent, like the
Oh,
mathematical constant e.
Could I do an exponent here?
Yeah.
Guess so. Never tried that. What's the case?
I think
on
it just
it?
be exp. Yeah.
Like that.
Yeah, probably lower cases, but probably better. Is that what is it not like? Oh, just one argument.
It takes exactly one argument.
So it just
yeah,
wants
of course.
yeah, you just want S5 divided by ki in the thing.
Oh yeah, I see. Yeah, I see.
There you go.
There's a little bit of a bump. Interesting. It's trying.
Have damped oscillation there.
It's not amplifying enough. Basically, what's happening is the number of steps basically become. Yeah, no, I'm not going to mention that because I go on forever. But you have to have this has to amplify and the signal that has to amplify enough to sustain the oscillation. What's happening here is that the amplification is not sufficient and the oscillation just runs out.
Yeah.
So.
And the last question,
yeah.
just like it was more steps between the signal and the signal acting to lead to oscillations.
Yeah, if you have more steps, it becomes easier in the sense I can drop the value of n. In fact,
there's a minimum at which even having a high end doesn't work.
Well, if I had an infinite number of steps, I can set n to 1, and it'll oscillate.
Oh, okay.
Yeah. So the more steps you have, the smaller the value n needs to be.
Is 5 steps sort of the magic minimum number, or is there?
Yeah, there is a magic number. Yeah, it's
okay.
This number of steps. Yeah,
it is this number of steps.
Yeah.
Okay, that's interesting. At least as far as these types of with mass action.
Yeah, it should be 4 steps actually. 1, 2, 3. It's 4 steps.
Oh, because the first one
from
is
the signal. Not including the last
okay.
one.
Got it.
Yeah, and you can prove that too actually, mathematically. We have a 3D plotter if you want to do 3D heat maps instead. The other thing, if you want to do lots of phase portraits in a grid and randomly pick parameter values. Oh no, sorry, what this is doing, sorry. It plots every species against every other species and then forms this grid of phase plots. I'll show you an example of that in a minute. Yeah, so in fact, I should have this here, I think. Where did I put it? That might be. It might be. Oh yeah, here we go. So you can generate fancy looking phase plots like this. This is basically, this is the oscillating model again, very similar, but notice it's slightly different. So we've got the same number of steps. And what I'm doing here is I'm plotting a phase plot. I'm plotting every species against every other species. So I'm plotting S1 against S3, S1 against sorry, what have I got here? S1 against S3, S1 against S4. What am I doing? What the axes here?
It looks like the axes are not labeled right.
No.
I don't know why, but
S1 against S3. Yeah, that should be S1, S2, S3, S. Oh yeah, this should be S3, S2, S1, oh, S4 or something. Oh, yeah, I didn't get the.
Both axes are weird.
I didn't get the axes right, labels right. I did this manually as well. So I'm using this thing called a subplot. This is a thing in Matplotlib. So I'm doing a 4x4 grid. I'm not bothering to plot the ones above the diagonal because they're just a mirror image. So I'm doing this check here. So anything above that, I don't bother to plot. And then I'm just pulling out the required data columns from M to plot each species against every other species. Okay, so I've got the labels wrong. So anyway, so if, you with Python you can do lots of things like this. I mean, in some cases we've tried to give you ready-made things that you can do without having to do all the programming. So, and this one gets the labels correct. Okay. So in fact, maybe if I did that instead. Let's try that. Oh, I know what it's after. Hold it TU. Okay, there. Okay, so now I got the right labels, but this that it doesn't cut off the top. Then notice there's a mirror image, right? If you look at it, that one there is the same as that one there, just mirror image. Okay, and the straight line in the middle is just the same metabolite with itself. So of course it's perfectly correlated with itself. Okay.
Another question about plotting hysteresis with positive feedback loops.
Say it again.
I was wondering how to plot hysteresis.
Oh,
by positive feedback loops.
We could do that. I have it in one of my blogs. I think that's using the plugins auto thing. Yeah, we can plot a hysteresis with positive feedback. I don't have it here, I don't think. Yeah, I mean, there's a case for having a sort of half-day, more advanced topics at some point to show all this stuff off in more detail.
Yeah.
But you can do history. You can do the bifurcation plot and show the hysteresis for positive feedback. Yeah. Anything else?
Yeah, someone else was like, "Oh yeah, that sounds interesting."
Yeah, we probably should do another half day at some point. Okay, I think that's it for me. I mean, the only other thing I've got here is using events to do perturbations, but you've seen that really. Okay, you're using the at function in antimony. The other thing I have here perhaps is you can actually use antimony to model just differential equations. So to model a differential equation, you just use this kind of syntax where you use a prime or quotation mark to indicate dy by dt. And so if I take this and just show you, do this, that's the exponential decay. The more fun one is I can do, well, I can do Lorentz attractor, okay, and I can write in all the differential equations for the Lorentz attractor, which is a chaotic system, and then run the simulation of that, and I get the Lorentz attractor output. Oh, one thing I just noticed I passed, which I meant to show you, was another trick thing you can do. Matplotlib has a way of plotting stream plots. There's something like this. So what this is this is actually sort of a hysteresis, showing you some level of hysteresis. The 3 dots represent the 3 steady states. The middle one is unstable. Top one, blue one, is the on state, and the red one is the off state. So this is 2 reactions that are inhibiting each other. Okay, and when you do that, they can exist in either an on state or an off state. And what these lines represent, it's 2 variables, y versus y versus x. If I were to place myself on any one of these trajectories and then did a simulation, I would follow this line in this phase plot, and this line will basically tells me I end up in the high state. On the other hand, if I started x and y here, I follow the line, I end up in the low state. Okay. If I'm very careful, I'm exactly on this line, x and y, I end up at the unstable state. And so I have this uses matplotlib. Basically what I'm doing is I'm generating a grid of points or right across this graph, X and Y points. That's what this grid is. Effectively, it's 200 points. So it's, well, it's 40,000 points. So 200 times 200. And then this is the model. Okay, and I'm actually running, I'm computing actually the differential equations here. I'm misusing antimony syntax. This is actually, if you think about it, this is actually represents the rate of change of X, and this represents the rate of change of Y. Initialize. I don't have to do a simulation here, but what I'm doing though is I'm creating now a grid from X and Y. And what's going to go in, I'm just sizing these two grids, U and V. I'm just making them the same size as Y and X. And inside this grid of U and X, I'm going to place the rate of change of X and Y. And so what this piece here does, it goes through every combination of X and Y, right? And that every combination of X, Y comes from this grid, and I'm setting X and Y to the values I get from the X, Y grid. I then compute the rate of change of X and Y just by using these calls and put them into U and V, and that's the data. I then use this stream plot, what's called a stream plot, to compute the streams themselves. And I just use these things here to actually plot a little round circle where the steady states are. Okay, so you can get very sophisticated, you know, if you're willing to try. This took a little bit of, it took me an hour or two to figure out how to do this. And then I realized how to combine Roadrunner with doing these kinds of stream plots, so you can do that. I guess the only last thing is parameter scans. The TUtils has a very simple parameter scanning function. This is for doing time course scans. So what it'll do, it'll plot time courses at different values, in this case K. You can do that. And so you can, this is a negative feedback system that's oscillating as well. And I'm changing the value of the Hill coefficient, right, over a number of different values. Then I'm plotting the simulations that results. You can see here, Hill coefficient of 1, we get the blue line, it's stable, and it becomes unstable as I approach H equals 8. If I went to H equals 9, it would probably be unstable and oscillate. So that's a very quick overview of some of the more advanced things you can do, but it'd be probably worthwhile doing a special, you know, half day at some point. We've talked about this before. So anyway, I think that's it for me. Any other questions? A lot of stuff there. I'll save this. I think this session is, this whole thing is saved on the drive.
Like, is the collab notebook that you were just editing also saved?
Yep, it's called
Okay.
Second Half of Session. I think it should be in Drive 2. Yeah.
Okay.
Yeah.
Just one of the people would be interested in her hysteresis. Someone actually measures hysteresis as part of their research. So if you could find your blog post about that, that would be. Or
Yeah,
whatever.
that's,
put that on
that's
Slack
right.
or something.
Let me see. Yeah, let me see if I can find it here. State bifurcation. Oh yeah, here it is actually. So and I have a little blog at blogsara.org. I just searched for bifurcation. This is an old one from 2016. I assume this still works. We should check this still works. I know the code. I know that the bifurcation code works. But I don't know whether it was anything changed in the syntax between then and now. But anyway, this is the model. Okay, this is actually a positive feedback system. You have to use something called a plug. We have this thing called R plugins, which adds extra functionality onto Roadrunner. And one of the things is a bifurcation package which lets you do hysteresis plots. It uses a thing called Auto 2000, which is pretty reliable. Anyway, you have to set up some various settings. You have to first of all access the plugin, and then you have set up these various settings, and then you just execute. And then when you execute, there's all this information that comes back on the bifurcations and so on. And we have a special method called plot bifurcation diagram, and basically that plots that thing there. Okay, so that's the network. So yeah, okay. So I guess I can put this in the chat if anybody wants to try it out.
Yeah, I actually
That's
already did that.
there,
So yeah.
And there are some other examples online as well, actually, that do this. In fact, you normally get a better plot than this. So I plotted this manually. If you actually do this plot, you actually get a better looking plot because it shows you where the stable points are and the unstable points are. So you actually get more information if you actually if you use the plotting function that comes with it. Okay. There's actually somebody also wrote a package, a separate package. Let me see, where is it? It was published in Bioinformatics. Where was it?
If it was published, you want to go to scholar.com or something?
It wasn't us that published it though. It was.
Oh, it wasn't that kind of published.
It was a group at PNL. I have to look it up. Well, there's one example of one of our bifurcation plots. Okay. I wonder where it went. Yeah, I don't know what it is now. Sorry, I can't find it now. Bifurcation, it was in Bioinformatics. Yeah, I can't remember now where it was. It was like 2 or 3 years ago. Oh, you were in communication with Lucian.
Which group? Do you remember which group it was?
You're at PNL. Oh, that's not it, is it? No, that wasn't it. Oh, that might have been it, actually. Might have been it. Might have been it.
Yeah.
You have to look it up. Okay. So Veronica, what's next then?
Open questions for anybody that might have them.
Open questions, yes.
I did hear in Veronica's breakout thing after my talk the other day, someone was asking just about like, how do I, when I find code online and it doesn't quite work and I can figure out what's went wrong, like what do I do? And there's different things you can do depending on how responsive the group that originally put it out there is. If it's on GitHub, you can always fork the thing and then do whatever you like with it at that point. GitHub is usually pretty good about making sure that everyone puts in a license in their work, and so you just need to make sure you follow the terms of that license. Often they are pretty permissive. But if you find a thing, if you find a problem, if you find a problem and you don't know what the solution is, you can always just file an issue on GitHub. If you aren't getting any response, or if you think you know what to do, you can fork it, try to fix it on your own copy, and then you can actually push it back it's called a pull request to the original repository. And if they are good about being somewhat responsive, they will then test that on their own. There may be automatic tests that will run, and they'll say like, oh, great. And then all they have to do is hit accept on your pull request, and then it's fixed in the main repository. If someone has just gone radio silence, then you just can fork it and start responding to things on your own, and you can monitor their issue tracker that's filling up with people with questions and say like, well, I've fixed this in my own fork. There are different things to sort of socially, it becomes more of a social problem than a technical problem. But on a technical level, GitHub will provide you the tools you need to either just ask questions, get things fixed, or to fix them yourselves on your own and help. You can help contribute by forking something and fixing it and pushing it back. I don't know if there are other questions or follow-ups about that, but that's the 2-minute summary of what you can do with stuff you find. Someone asked about spatial changes. Yes. Yes, if you want to do things in space, you should use a spatial simulator. Again, there's vCell. Let me see if I can find a link to vCell.
This would be a good place to plug tomorrow's symposium because we'll hear about SBstoat and also Compusal 3D.
Okay.
Do you want the screen?
So here's vCell. Compusal 3D is obviously also 3-dimensional. It's more, it does agent-based models. So it's usually talking about like like a field of 1,000 cells that are all doing something. Each cell might have an SBML model in it, or each cell might have even a very simple model in it, or just different characteristics. Yeah. Okay, we got all sorts of questions here. That was a spatial thing. Example publication that uses scaled sensitivity with the collaborator you mentioned, who can make percentage changes in gene expression, measure relative change in metabolites. I don't have the answer to that question in particular. Herbert, do you know?
What's that?
Is there an example publication that uses scaled sensitivity?
Oh yeah. No, I was just thinking. Yeah, we haven't published ours yet.
Okay.
The experiments are currently being done. I mean, there are a lot of publications where they have measured these sensitivities, but you can use lots of different techniques. You can use inhibitors. You can change gene expression. You want to look up metabolic control analysis experimental or something on Google. You'll find a lot of papers, mainly European papers. So.
All right. Okay, there's a couple more technical things. Initialization of compartments in the model. All you have to do is define a compartment, and then you just say that compartment equals 5 or whatever. Actually, I put my little, very tiny compartment example on the Google Drive, like in the root directory, like all the days are there, and then it's just next to that, it says something like compartment-y thing. And yeah, so that if you have a more specific question about how to initialize a compartment, basically you initialize it just like you initialize a species. You say S1 equals 5, cell equals 10 or something. So that's that.
That other question.
Yeah, using iteration.
Yeah, I'm looking at that now.
Okay. Oh, the iteration thing?
Yeah.
Group size. For the plot array, it could be just that we haven't given that as a argument in plot array.
Let me see.
If there's something that, in general, if there's something that Roadrunner or Tellurium doesn't do for plotting, you can always just pull the data out and plot it yourself by hand with matplotlib.
Yeah.
And then it becomes adventures in matplotlib more than adventures in Tellurium. But matplotlib will definitely have fig size arguments in there, even if we've forgotten. And if there is a particular thing you would like, you can file an issue and say like, hey, can you add fig size to this function? And I can do that. It probably won't even be that difficult.
Yeah, I confirm that's not happening.
Okay. Or it may just, does it take it as an argument and then ignores it? Or does it complain about it being an argument?
Ignoring it.
Okay. So that's just a bug, and that's another thing.
Yeah, we need to look at this. I need to look at some of these plotting things, because they've a lot of people have contributed to the plotting stuff, and it's sort of changed over the years. I mean, I can show you one example what I did just now. Let me just share this with you, which did work. So this example here was just to show a stochastic simulation. And this is where I am using the plot array. So what I'm doing is I got the model here, and I'm going to do 50 simulations. And so I'm running, there's a thing called the Gillespie that does the stochastic simulation. And all I'm doing is plot array show equals false. That's all I'm doing. I wonder if it's, let me just check here. I'm just trying on my other screen. Oh, I know. Yeah, that should work, what you did, I think. Just confirm. I'll bring this over here so you can show me what I'm doing. So this is some of your code. I'm just going to add a random number to that. There you go. Yeah, that worked. So what were you doing that didn't quite work? So one thing I noticed, I commented that out. Yeah, that works. So what was it that you? What the hell is that right here? What was it that you did? That should have worked. Yeah. This is Christian Solis Calero. I have it working there. I don't know what happened with yours. You had a line style and labels. I wonder if that made a difference. Shouldn't do. Right, I'll post this into the chat. Try it on the one you've got. Oh, so I know there was some people who wanted to go over some of their models. What's the schedule for tomorrow, Veronica?
Tomorrow is just the symposium speakers.
So it starts at what, 8 our time?
Yep.
And goes on to
another 8 to noon, or?
Yep, 8 to noon.
8 to what?
12 p.m.
12. Oh, okay.
Noon, yeah.
So, 4 talks. Yeah, right. When do we have time? It might be a good idea maybe to schedule some time next week for people, now that you've tried out Tellurium and Roadrunner. Maybe you can get in touch with us and we can schedule some time next week for anybody who wants to go over their model and they have some problems. I think, would that work for people? You know, at least one of you wants to go over the over a model they have.
Yeah, particular thing.
We could do that.
I mean, I also have time this afternoon if.
Oh yeah, well, this afternoon too as well. Yeah,
Yeah.
of course. Yeah. I'm fully booked this afternoon. But yeah, this afternoon would work as well for anybody. So
You don't need Herbert.
yeah, I don't even.
All right, there's a Compusal 3D question that I don't know anything about. It says, is there a way to relay the distance between cells releasing and uptaking chemicals in tellurium to include this in the concentration changes?
Is there a way to relay distance between cells releasing and uptaking chemicals? Is there a way to relay the distance between cells? I think so.
I think there
you
is.
can
I
do
mean,
anything you want. I think you can hook up the model
Yeah.
in tellurium in any way you want to the outside. So
I
it's
don't
something you
specifically
can
know
ask,
how you connect things up, but I mean, presumably they're already hooked up in some ways. Otherwise, there'd be no
yeah,
communication at all. But
you do a manual wiring.
yeah,
You wire things up in the way you want them to go. So okay, so Nosheen, Fatima says what time, you guys?
do you want to give us like a lunch break in one-ish?
It sounds like you're in Iran, are you, Fatima? Oh, no, sorry, not Nosheen. Oh, where are you?
Yeah, like when.
Oh, not Iran. New York, NYS. Yeah.
New York
so,
State.
Yeah, so 1 o'clock would be 4 o'clock for you then, yeah. But it is a Persian name. That is right. Yes, it is. So what's 4 o'clock like for you? Your
local
time.
yeah, like in another hour.
Sounds good. Says, yeah.
Sure. Yeah.
Yeah.
We can probably just use the same Zoom URL if we want.
That's right. One EST.
One
yeah.
Western.
It's 1 p.m.
Pacific,
EST.
so Western.
4 o'clock. No, sorry, 4 o'clock EST.
Like
1 o'clock
Eastern.
PD.
Yeah, there you go.
Yeah. Good. Okay.
Dun-dun-dun. Veronica, would you be free at that time also or not?
I can be free at that time.
Okay. Might be nice to have a, a little bit of a backup. Have we missed any other questions? Does anyone have further questions about things?
Yeah.
Sounds good.
Anything else?
Let me see if I can post a link directly to that compartment thing.
You doing one last thing, Lucian, or something?
I was just gonna yeah, copy something into the chat if I can get to the chat. There we go. So that was the very basic thing on compartments that I had put together, and I'm happy to answer other questions about that if you have them. I think also someone on the Slack was having trouble actually finding your stuff. Let me go. Oh, lecture materials day 4. No, sorry, not day. Yeah, day 4. The only thing I see
Yeah,
in
so-
lecture materials day 4 is the other thing. Go ahead, Veronica. Sorry.
I had created a folder there thinking we could upload Herbert's like live coded examples from today, but actually he already had them uploaded in day 2 in the first session. So
Yeah.
the materials are there.
So the thing that he's working on right now is in the day 2,
Yeah,
day 2,
Yeah.
session 2,
Yeah.
session 1.
Session 1.
session
Oh, the
1.
second half of session.
Okay. So it's in this. All right, got it. Yeah, put that in the chat also.
All right, is that it? Okay, and till tomorrow then. We'll see you tomorrow. Well, some of you will see some of the others at 4 and see the rest of you tomorrow.
Yeah, sounds good.
Okay, I know.
Thanks everyone for coming.
Hey, everyone.
Because we can stop the recording also. Just hit stop.